Consider this problem. A container is filled with N2, O2, and argon gas. The partial pressures of N2 and O2 are 615 and 125 torr respectively. If the total pressure is 785 torr, what is the partial pressure of argon? Now you need to be familiar with Dalton's law of partial pressures, which basically states that the total pressure is the sum of all of the individual partial pressures. So that is the partial pressure due to the N2 gas, the partial pressure of O2, plus the partial pressure of argon. So every substance exerts its own partial pressure, and the sum of all of these individual partial pressures is equal to the total pressure. Now we're given the total pressure, it's 785 torr. We also have the partial pressure of N2, which is 615, and the partial pressure of O2, which is 125. So now all we need to do is calculate the partial pressure of argon. So we need to add 615 and 125, which is going to be 740. Next, we need to subtract both sides by 740. 785 minus 740 is 45. So the partial pressure of argon is 45 torr. And so this question wasn't that bad. It's very easy to find the partial pressure of a gas if you know the partial pressures of all the other gas and if you know the total pressure. Number 2. A 2-liter vessel holds 3 moles of nitrogen and 2 moles of oxygen gas. What is the mole fraction of N2 and O2? So let's start with that. If you want to find the mole fraction of substance A, it's equal to the moles of substance A divided by the total moles of substance A. You can also calculate the mole fraction of substance A if you know the partial pressure of A and if you know the total pressure. Since pressure and moles are directly related, it works out the same way. So if we want to find the mole fraction of nitrogen gas, we need the moles of N2 and we need to divide it by the total moles, which in this example consists only of N2 and O2. So there are 3 moles of nitrogen gas out of a total of 5 moles because there's 2 moles of oxygen. So it's 3 out of 5, which as a decimal is about 0.6. So that's the mole fraction of N2. So 60% of all the molecules in this vessel consist of nitrogen gas. The mole fraction of O2 is going to be the moles of O2, which is 2, divided by the total, which is 5. 2 out of 5 is 0.4. So the other 40% consists of oxygen molecules. So you could think of mole fraction as the decimal equivalent of a percentage. Now let's move on to part B. If the total pressure inside the container is 1000 torr, what are the partial pressures of N2 and O2? So let's start with the partial pressure of N2. You could find it by taking the mole fraction of N2 multiplied by the total pressure. The mole fraction is 0.60. The total pressure is 1000. So therefore, the partial pressure of N2 is going to be 60% of the total pressure, which is 600 torr. Now to calculate the partial pressure of O2, it's going to be the mole fraction of O2 times the total pressure. The mole fraction is 0.4, total pressure is 1000. So the partial pressure of O2 in this example is 40% of the total pressure. So that's going to be 400 torr. And as you mentioned before, the sum of all the partial pressures must add to the total pressure, which is 1000. 600 plus 400 is 1000. Try this problem. The partial pressure of helium is 400 torr. If the total pressure is 550 torr, what is the mole fraction of helium? The mole fraction of helium is simply the partial pressure of helium divided by the total pressure. We know what the partial pressure is. It's 400, and the total pressure is 550. So we just got to divide these two numbers. So this is going to be about 0.727. So that's the answer. So 72.7% of all of the molecules in this problem will consist of helium. So that's what the mole fraction tells you. It tells you the percentage of this substance in the container. Number 4. The mole fraction of neon is 0.27 inside a 2.8 liter container. If the partial pressure of N2 is 350 torr, what is the total pressure inside the container? So we could start with this equation. The partial pressure of neon is equal to the mole fraction of neon multiplied by the total pressure. Now we know that the partial pressure is 350 and the mole fraction is 0.27. So with that information, we can calculate the total pressure. It's simply going to be the partial pressure divided by the mole fraction. So it's 350 divided by 0.27. And so that's going to be 1,296.3 torr. So that's the total pressure in this example. And if you want to, you can convert it to ATM. Number 5. A room is filled with N2, O2, and CO2 gas. The mole fractions of N2 and O2 are 0.77 and 0.20 respectively. If the total pressure inside the room is 740 torr, what is the partial pressure of CO2? The sum of all the mole fractions have to add up to 1. So the mole fraction of N2 plus the mole fraction of O2 and the mole fraction of CO2 must add up to 1 because it's based on a percentage, and 100% is equivalent to 1. The mole fraction of N2 is 0.77. For O2 it's 0.20. So we need to solve for the mole fraction of CO2. 0.77 plus 0.20 is 0.97. And 1 minus 0.97 is 0.03. So that's the mole fraction of CO2. So 3% of all the molecules in this room consist of carbon dioxide. So if there were 100 molecules, 3 of those molecules will be CO2. 77 of those molecules will be N2, and the other 20 would be O2. So now that we have the mole fraction of CO2, how can we use it to calculate the partial pressure of CO2? So now we can use this equation. P of CO2 is equal to the mole fraction times the total pressure. So it's going to be 3% of the total pressure. So it's 0.03 times 740. So the mole fraction, or rather, not the mole fraction, but the partial pressure of CO2 is 22.2 torr. And this is the answer to the problem. Number 6. 20 grams of N2 was mixed with 25 grams of O2 inside a 3.7 liter container at 300 Kelvin. What are the partial pressures of N2 and O2? So how can we find the answer? We can use this equation. PV is equal to nRT. So if we use the moles of N2, that's going to give us the partial pressure of N2. So if you divide by V, you'll see that P is equal to nRT over V. So if you use the moles of N2 times RT and divided by V, you're going to get the partial pressure of N2. And if you want to get the partial pressure of O2, make sure you use the moles of O2. If you want to get the total pressure, then you need to use the total moles. So basically, the subscripts have to match. So let's start with the partial pressure of N2. So first, I need to find the moles of N2. I have 20 grams of nitrogen gas, and the molar mass of N2 is 28.02. It's 14.01 times 2. So there are 0.7138 moles of nitrogen gas. So now I'm going to calculate the partial pressure of N2. So it's the moles of N2, which is 0.7138, times R, which is 0.08206, multiplied by the Kelvin temperature of 300, divided by the volume, which is 3.7 liters. So you should get 4.749 atm for the partial pressure of N2. Now let's do the same thing for the other gas. So let's calculate the moles of O2. So we're given 25 grams, and the atomic mass of oxygen is 16. Multiplied by 2, the molar mass of O2 is 32 grams per 1 mole. So 25 divided by 32 is 0.78125 moles. So now let's use this equation to calculate the partial pressure of O2. So keep in mind it's the moles of O2 times RT divided by V. So that's going to be 0.78125 multiplied by the R value of 0.08206 times the Kelvin temperature of 300 divided by the volume of the container, which is 3.7 liters. So the answer that I have is 5.198 atm. So I'm just going to write that somewhere on the top. So that's it for part A. So now we can move on to part B. Calculate the total pressure inside of the container. Now there's only 2 gases in this problem. So therefore the total pressure is simply the sum of those 2 partial pressures. So all we got to do is add up 4.749 plus 5.198. So the total pressure is 9.947 atm. So that's the answer to part B. Now let's move on to part C. What is the mole fraction of each gas? So the mole fraction of N2 is going to be the partial pressure of N2 divided by the total pressure. So that's 4.749 divided by 9.947. And so that's 0.477, which is basically 47.7%. However, the answer that you should report is that value. Now let's calculate the mole fraction of O2. So that's going to be the partial pressure of O2 divided by the total pressure. So that's 5.198 divided by 9.947. And so that's going to be 0.523, which is equal to 52.3%. And so that's it for this problem. So now you know how to calculate the partial pressures, the total pressure, the mole fraction, and things of that sort. Number 7. 35 liters of neon gas at 27 degrees Celsius at 1.2 atm was mixed with 44 liters of argon gas at 32 Celsius at 1.3 atm into a 50-liter tank at 30 Celsius. What is the partial pressure of each gas in the tank? And what is the total pressure inside the tank? So before we put it into the tank, the pressure of neon was 1.2. Once we place it into the tank, it's no longer going to be 1.2. For one reason, the volume changes from 35 to 50, and the temperature changes from 27 to 30. So the partial pressure of neon is not going to remain 1.2. And the same is true for argon. It's not going to stay at 1.3. The partial pressure is going to change. However, the moles of neon and argon that we add into the tank, that's not going to change. So the amount of moles that we had of neon before we added into the tank, which we can find based on that information, is going to be equal to the amount after once we put it into the tank. The moles is not going to change. So let's use this equation, PV is equal to nRT, to calculate the moles of neon. The pressure is 1.2 atm. The volume initially is 35. And the temperature is 27 Celsius, but if we add 273 to that, it's going to be 300 Kelvin. So N is going to be 1.2 times 35 divided by 0.08206, and then take that result divided by 300. So therefore, we have 1.706 moles of neon. Now let's do the same for the other substance. Let's use the same formula, PV is equal to nRT. So we're going to use this information here. So the partial pressure of argon is 1.3. The volume initially is 44 liters. R is not going to change. And the temperature is 32 Celsius plus 273, so that's 305 Kelvin. So it's going to be 1.3 times 44 divided by 0.08206, and then divide that by 305. So the moles is 2.285 moles of argon. So I'm going to rewrite this on top so I can use it as a reference. Okay, I did not want that to happen. So we have 1.706 moles of neon and 2.285 moles of argon. So now what should we do next at this point? How can we use this information to find the new partial pressure in the tank for each of these gases? We can use the same equation. PV is equal to nRT. The only difference is we're going to use a new volume and a new temperature. So now let's calculate the partial pressure of neon. So the new volume is 50 liters, and the moles, we have to use it for the same substance, neon, which is 1.706. Now the new temperature is 30 plus 273, so that's 303 Kelvin. So the partial pressure of neon is going to be 1.706 times 0.08206 times 303 divided by 50. And so that's going to be 0.8484 atm. So that's the partial pressure of neon. Now let's do the same to calculate the partial pressure of the other gas, argon. So the volume is going to be the same. The moles is going to be different. It's now 2.285. And everything else is the same, R and T. So it's 2.285 times 0.08206 times 303 divided by 50. So the partial pressure of argon is 1.1363 atm. So now that we have the partial pressure of each gas, we can now calculate the total pressure, which is the sum of these two partial pressures. So it's 1.1363 plus 0.8484. So the total pressure is 1.9847 atm. And so that's it for this problem. What is the partial pressure of each gas after the stopcock between the two flasks is open? Assume the final volume is 5 liters. Now let's focus on neon. The volume is going to increase from 3 liters to 5 liters. Anytime the volume goes up, the pressure goes down based on Boyle's law. So as soon as the stopcock is open and as the volume goes up, the partial pressure of neon is going to decrease from 765 to a smaller value. Now the volume of helium is going to change from 2 to 5 liters, and so the pressure is going to decrease. Now all we need to do is use Boyle's law for each gas separately. Let's start with neon. So the first partial pressure of neon is 765 before we open the stopcock, and the volume is 3 liters. We need to find the new partial pressure when the volume is increased to 5 liters. So it's going to be 765 times 3 divided by 5. So once it's open, the partial pressure of neon is now 459 torr. It decreases. Now let's do the same thing for helium. Before the stopcock is opened, the partial pressure of helium is 625, and it has a volume of 2 liters. Now once it's open, the volume increases to 5 liters. So it's going to be 625 times 2 divided by 5. So the new partial pressure of helium is 250 torr. So for this type of problem, all you need to use is Boyle's law for each gas separately. You just need to find out what the new volume is going to be and then calculate the new pressure. And then if you need to find the total pressure, simply add these two values. So the total pressure after the stopcock has been removed, or after it's been opened, it's 459 plus 250, which is 709 torr. And so this is the answer.